Hi everyone, this is Austin Hoggett here to give you another OpenStax Intermediate Algebra lecture. And today we're going to be talking about the addition, subtraction, and multiplication of radical expressions. In previous sections we've discussed the product rule, which allows us to simplify most radical expressions, which is critical for this particular lecture. We're going to start with the addition and subtraction of like radicals, and then moving into the more complicated scenario of how we multiply them together. The use of polynomial multiplications is also going to be introduced in another section. For addition and subtraction of radical expressions, it's much the same as when we're trying to add and subtract like terms. We have to ensure that the variable and exponent match. We've talked about the connection between exponents and radicals before. When we talk about like radicals now, we mean to say that they have to have the same index and the same radicand. The index is often found in the top left corner of our expression, where the radicand is what's underneath. So for example, the way in which we would add together expressions like 2x plus 3x to get 5x would be the similar method that we use to add together something like 2 square root of x plus 3 square root of x to get 5 square root of x. These are like radicals, meaning that the expressions underneath here have to be the same and the index of the root must match. It's not always going to be obvious that we have like radicals, and so on occasion we'll need to use the product rule to be able to simplify before being able to follow up with a solution. Let's take a look at some examples. Here we have what are two fairly simple examples where it's quite obvious, hopefully, that we have like radicals. In part A, 2 square root of 2 minus 7 square root of 2 can be combined by looking at their coefficients. In this case, we add together 2 minus 7 to get the solution negative 5 and keep our square root of 2 involved. For part B, we have, again, obviously roots that match cube root of y. And so we can add them quite easily together by their coefficients, positive 5 and positive 4. Solution being 9 cube root of y. So as I mentioned, it's not quite obvious all the time that we have like radicals. Let's look at some scenarios where we have to produce a simplified version before we can even determine if addition and subtraction is possible. Here's an example with just numeric values. So I'm asked to add together the square root of 27 plus 4 square root of 3. Initially, it's not quite clear that I can even add these together because the square root is not the same in each case. By simplification, though, we can think of square root of 27 as the product of 9, the perfect square factor, times the non-perfect square factor 3. So this goes back to the product rule that we discussed in previous sections and will be critical for answering a lot of the questions here. Once we've sort of broken our expression apart, we can see that what will be left over is 3 square root of 3 plus 4 square root of 3. My perfect square factor 9 reduces and comes out from underneath the radical. Our trash factor 3 stays within, allowing me to actually add these two expressions together. They're now like radicals, and so we add them by their coefficients to get the solution of 7 square root of 3. So we can use this particular setup in instances not only where we're asked to add or subtract expressions with numeric values, but also for variables. So let's look at some more examples. In this case, I'm asked to, again, simplify. And although there are some similarities between the expressions, they're both square roots. They both happen to have m squared, but the coefficients underneath those radical expressions are different. So I can't immediately add them. What we would again try to do is simplify using the product rule. Let's start with the first term here. I have 9 times the square root of 50m to the second. In this case, what we can do is identify from the expression underneath 50m squared what the perfect square factors and non-perfect square factors are. 50 we could break apart into 25 times 2. where 25 is the perfect square and 2 is our non-perfect square factor. M squared, being a square term, obviously is already going to be part of our perfect square factors. And so we can split them apart in this way. We split our roots so that we can then satisfy the other portion of this question, which is what is the perfect square of 25m squared? So 9 is still involved here. We get the square root of 25 is 5. M squared, when we take the square root, just gives me m. For my second expression, we follow a similar pattern. We want to split the square root of 48 into, again, two parts. Our perfect square factor in this case is going to be 16 m squared, and our non-perfect square factor is 3. So you'll notice in this case that once I do my split, the perfect square factor 16m squared will become 4m, and the square root of 3 stays underneath the radical. We can't actually add these two expressions together because they're not going to be like terms. They both have a variable m involved, but they have different square roots. To finish the problem, though, I need to simplify a little bit further. My coefficients for the first and second term are going to end up being 45m square root of 2 minus 24m square root of 3. Since they can't be added or subtracted in this case together, we're done. So we're not always guaranteed that an expression like this will be able to be simplified further, but we'll need to use the product rule to determine that. Let's look at some more examples where we're involving now the process of multiplication. Multiplying radicals has been shown using the product rule already. We'll extend that idea here along with the distribution property in some cases. While the multiplication process is given by this product rule, for instances where we do multiplication, it's really common that we'll actually have to use this product rule more than once. In other words, let's imagine I have some example like the square root of 2 times the square root of 8. When I multiply them together, by the product rule, I should get the square root of 16. But this isn't quite finished because I can simplify that to get a solution of positive 4. Likewise, if I multiply together something like the square root of 10 times the square root of 2 to get the square root of 20. I'm not really finished because the square root of 20 can be broken back apart using the same product rule. And so it's really common that we end up with a solution by multiplication that then needs to be reduced. And so ultimately we'll boil it back down to 2 square root of 5 for the solution. Let's look at some more examples and see how this gets more complicated as the distribution comes into play. Here's a couple of examples looking at monomial terms. So in part A, I'm asked to find the product of 6 square root of 2 times 3 square root of 10. By the commutative property, I can sort of rearrange either mentally or, as I write it down here, the process of multiplication. I'm going to look at the coefficients, the product of which will give me 18. And according to the product rule, again, we just saw that square root of 2 times 10 should give me the square root of 20. So just as before, we can break the square root of 20 back down using a different pair of factors. We want to split it into the square root of 4 times the square root of 5. So we initially multiplied two square roots together to get the square root of 20, and then we break it back apart here, reducing the square root of 4 to the whole number value 2 here gives me a coefficient for the solution of 36 times the square root of 5. In part B, we can follow a similar step-by-step process, looking at the coefficients. The product of negative 5 and negative 4 should give me positive 20. The two cube roots can be multiplied together to give me the cube root of 4 times 6, or the cube root of 24. In this case, we're looking for cube roots, and so the split is going to end up being for perfect cubes and non-perfect cubes. The largest of which in 24 would be 8. And my trash factor is 3. So the cube root of 8 reduces nicely to give me positive 2, because that's what we raised to the third power to get back what's under the radical. 2 times 20 should get me to 40 for the coefficient, and cube root of 3 stays underneath the radical. So there we have our solution. These monomial examples demonstrate how we can multiply the coefficients together and deal with the process of multiplying and then simplifying our radicals as we extend the number of terms in a multiplication problem. Again, the distribution property comes into play, so we just have to repeat this process iteratively. Let's continue with some more examples. In this case, I've got another pair of monomials, only in this one, I've got a slightly more complicated set of expressions underneath the radical. So let's do one more of these before continuing further. Again, looking at my coefficients, I've got the product of 10 times 4 giving me 40. My two square roots can multiply in this case to give me the square root of 6 times 3, which is 18, p to the third times p to the first, giving me p to the fourth. What is this expression going to split apart into? So again, I want to split it up into perfect squares and non-perfect squares. Inside of 18, I would split it by using the factors 9 and 2, where 9 is the perfect square and 2 is the trash factor. Since p to the fourth has an even exponent, it'll be divisible by my index. And so we can find the root very quickly. It's a perfect square already. So the square root of 9 is 3. The square root of p to the fourth is p squared. As usual, my trash factor stays underneath. Simplifying the coefficient gives me my solution here of 120 p squared square root of 2. So finally, let's extend this idea and introduce the distribution property. In these cases, we'll have either 2 or more radicals being multiplied together by that distribution pattern that we've seen before. Take a look at part A here. I'm asked to find the distribution of the square root of 6 times 1 plus 3 square root of 6. Our distribution pattern tells me that I should multiply the first term, square root of 6, times each of the terms inside the parentheses like this. So just as we would expect usually, we can rewrite this as square root of 6 times 1 just gives me the square root of 6, so I'll leave it in its simplest form. In the second case, I get 3 square root of 6 times the square root of 6. The product rule tells me that the square root of 6 times itself should give me the square root of 36. Well, the square root of 36 happens to break back down to 6 because it's a perfect square. And I'm left here with 3 times 6, or 18, plus the square root of 6 for my solution. One thing I want to point out in this example that shows up quite a bit when we start talking about distribution of this type is that instances where I have a square root multiplied by itself, as in the square root of 6 times the square root of 6. What we produce in doing so is a perfect square term. So imagine, if you will, that I can rewrite this actually as an exponent. What we just saw, though, is that really all of this boils back down to whatever my base value under the radical would be. And so it's very common to take advantage of this fact when we are doing multiplication problems to make quick work of instances like this, where we're trying to multiply some square root by itself. I can sort of jump over the fact that the product here gives me the square root of 36 and recognize that an exponent and radical cancel each other out here. Let's take a look at part B as well. In part B, I have another distribution similar to before, where we take the term on the outside of the parentheticals and multiply it by everything on the inside. So we start with negative 2 times the cube root of 4, and then we have the cube root of 4 times the negative cube root of 6. In the first case, we can just sort of rewrite the expression as it's given. The cube root of 4 doesn't simplify, and so we can leave that term as is. For our second terms, we have no coefficients other than 1 and -1. The product there gives me a negative outcome. But the cube root of 4 and the cube root of 6 can be multiplied together to give me the cube root of 24. We've seen this example 4 split up into the following terms. We could have the cube root of 24 split into the cube root of 8 times the cube root of 3, where the cube root of 8 simplifies to give me 2. So we actually can't add these together. However, we do get the following result. Notice that, again, my radicand expressions are different, so I can't combine these in any meaningful way, even though the index of my root matches. Let's look at some more examples that include not just the basic distribution we see here, but some type of FOIL method. In these two cases, I have a product of binomials, and so I can apply the FOIL method in order to figure out what the product should be. Following my arrow pattern here, we should take 3, multiply by the 2 terms in the second parentheses, and we turn around and do the same thing for the second term. In this case, I get the product of 3 times 4 is 12, and the other expressions here I'll write out more explicitly because it can be quite difficult to figure out what should the sign of my expression be, and to recognize that we end up with some duplication. So notice that, as is the case in most binomial multiplications like this, my two expressions in the middle are actually going to be able to be combined together. They both have a square root of 7 along with some coefficient. We'll also talk about how to find the product of those last two terms. -2 square root of 7 times -2 square root of 7 does in fact create another perfect square. Simplifying the middle bit here first, however, again, should allow me to see that this is going to end up being just one single term. The coefficients of which will be -6 square root of 7 and -8 square root of 7. If we combine those together, we'll get -14 square root of 7. But we still have this last term to contend with. The coefficients are both -2. When we multiply them together, we should get +4. What we showed last time is that multiplying a square root by itself produces a perfect square. Since the exponent and radical here will cancel each other out, I actually just end up with 4 times 7. Since the product of 4 times 7 gives me 28, I'll add that together with my first term here to produce the final answer. We get 40 minus 14 square root of 7 for our solution. In part B, we have a similar type distribution pattern that can be done. Using the FOIL method, we end up with something like the cube root of x times the cube root of x, the cube root of x times 4, -2 times the cube root of x, and then -2 times 4. The first term here, cube root of x times itself, can be rewritten slightly as the cube root of x squared. It does not exactly match the pattern that we showed here. Since this does not create a perfect cube, it will not pop out from underneath the radical. We can multiply them together using the product rule as we would normally. And again, the two middle terms here create some kind of like terms that we can combine. So 4 cube root of x minus 2 cube root of x should be combined at the end. Since these are like terms, we can add them together and get something like 3 cube root of x squared plus 2 cube root of x minus 8 for the solution. Now, partly I'm not quite finished because I've produced 3 terms instead of 2 as expected, but the first term here is x squared as opposed to just x. And so, although it looks like we should be able to combine these further, we really can't. The three terms are not like radicals, and so we're finished. Let's look at some more examples here of multiplication. These examples will involve the special product rules that we've seen before, highlighted here, known as the binomial squares and product of conjugates. These particular patterns make quick work of problems like this, even involving the square roots. So this happens to match the following pattern up here, a plus b squared, which means the result should give me 2 to the second plus 2 times 2 times the square root of 3 plus the square root of 3 squared. Now, this is our solution. It does need to be simplified somewhat, but we didn't have to follow the FOIL method to get to that answer. So reducing 2 squared is 4. Our middle coefficient is going to be 4 square root of 3. Our exponent and radical cancel each other out for the last term to give me just plus 3. And so finally we get a result by adding our two constants together of 7 plus 4 square root of 3. You'll find these special products are quite handy for making quick work of products like this, especially if they show up in contexts other than just finding the operation. Lots of times you'll see these types of products inside of an equation that you need to solve. And so the more efficiently you can find that product quickly and easily, the better off you'll be. Let's look at just a couple more examples of the different patterns. In the next case, we have a difference. This is in the form a minus b raised to the second power, which has a very similar formula to the last example. Instead of plus 2ab, we have minus 2ab though. So that's really the only difference here, is that my middle coefficient is negative. Since that is the case, for our solution here, we should have a as 6 and b as the square root of 5. Replacing our values in the formula looks something like this. So as before, once we've got our substitutions, we can go through and simplify. The first term here should give me 36. My middle coefficient is going to be negative 12 square root of 5. And again, the exponent and radical canceling each other out here leaves me with plus 5 at the end. 36 plus 5 gives me 41 minus 12 square root of 5 for the solution. One last special product here to show. In this case, we have a product of conjugates. Remember, conjugates use the same terms. The only difference is the sign between them. So they come in the form a plus b times a minus b. And the solution is always a difference of squares. So in this case, the product of 5 minus 2 square root of 3 and 5 plus 2 square root of 3 is going to give me 5 raised to the second minus 2 square root of 3 raised to the second. We would get 25 in the first case. And for the second term, we can raise each of those values to the second power. So 2 squared gives me 4. Square root of 3 squared gives me 3. Again, the root and exponent cancel each other out. Well, this is just a numeric value. We end up with 25 minus 12 for the solution here of just 13. One thing to comment here is that because we used the product of conjugates here, notice that our solution didn't involve any square roots at all. We'll take advantage of that fact later on when we talk about rationalization. In other words, when we have division by square roots, we'll sometimes use this particular special product rule to eliminate those radicals in the denominator, referred to as rationalization.